Welcome to the Deep Dive. Today we're definitely moving past the basics, leaving the shallow end of React tutorials behind.
Yeah, we're diving straight into the strategies that, senior developers actually use day to day.
Exactly. This dive is really for anyone who wants their applications to feel amazing for the user, not
Yeah.
just, not just work.
Right, because when you're scaling things or you're under pressure, just knowing about state and props, it's not enough.
We've been digging through some expert performance guides,
Yeah.
going way beyond the standard docs here.
Focusing on those real-world tactics you see in big production apps.
And the mission today is tackling this subtle but honestly really persistent problem.
Mhm.
Most developers know about the virtual DOM, maybe,
Mm-hmm.
but they often miss the specific target optimization patterns that stop those, like, cascading re-renders that kill performance.
It's about moving from guesswork, from just thinking your app is slow, to making actual strategic, data-driven decisions.
Okay, let's unpack this then. What really stands between a sluggish React app and a genuinely fast one? And I think, for us, that story has to begin at the foundation, right? The virtual DOM.
Absolutely. The virtual DOM, or VDOM as people call it, it's basically just a lightweight JavaScript object. Think of it like a blueprint that mirrors the structure of the real browser DOM.
An intermediary.
Exactly, an intermediary. And the whole performance gain comes from avoiding expensive, direct changes to the actual browser layer all the time.
Right, because touching the real DOM is slow. But the magic, the real genius of React is that diffing algorithm that works with the VDOM.
Yeah.
How does it get that efficiency? What stops it from, grinding the browser to a halt?
Well, it boils down to some clever shortcuts, some heuristics. If React had to compare every single old node to every single new node every time something changed, the complexity would be terrible. Would be
That's right.
just unusable.
Yeah.
And instead, React uses a heuristic ON algorithm, much, much faster.
Oh, that's fantastic.
Yeah.
So what assumptions is it making to get that kind of speed boost?
There are two main ones. First, it assumes that if you change an element's type, like a div becomes a span, they're going to produce completely different trees of components underneath. So React doesn't bother trying to compare them deeply. It just tears down the old tree and builds the new one from scratch for that section.
Okay, that makes sense. What's the second one?
The second one is crucial for optimization, the key prop. When you map over an array to create a list, React assumes that key you provide is a stable identifier. It uses it as a hint to figure out which elements haven't changed, which ones were just reordered, and which ones are genuinely new or removed.
Gotcha. So that key prop isn't just for React's internal bookkeeping, it's fundamental to the diffing efficiency.
Absolutely fundamental.
So, okay, let's walk through it. A piece of state changes somewhere in my app. What are the steps React takes? That whole choreography before the user sees an update.
Right. That's called reconciliation. And it happens in three main phases. First is the render phase. This is where React calls your component functions, figures out what the UI should look like now, and generates that new VDOM representation.
Okay, step one, build the new blueprint.
Step two is the diffing process. React takes the new VDOM tree it just built and compares it to the previous VDOM tree. It identifies exactly what changed.
Finding differences.
Yep. And then finally, step three is the commit phase. This is where React takes only those changes it identified and applies the minimal necessary updates to the real browser DOM.
Okay, render, diff, commit. And this brings us to what feels like the critical point for optimization. If I change some state way up high in the component tree, React's default behavior is kind of reckless. It just re-renders everything below it. Is that right?
That's exactly right. By default, a state change is the only thing that triggers a re-render. And when a component re-renders, all its descendants follow suit. It doesn't matter if their props changed or not. It's React playing it safe, essentially. It prioritizes making sure the UI is definitely synchronized with the state, even if it means doing extra work.
So it prefers rendering too much, over-rendering too little, and potentially showing stale data.
Precisely. And this leads to a really important point for us developers. Our main job isn't usually about eliminating all re-renders. That's often impossible or unnecessary. Our job is to find and optimize those critical renders, the ones that cascade down unnecessarily and actually hurt the user experience.
Okay, that makes perfect sense. And that leads us right into these hidden optimization patterns, the things that bridge the gap between just knowing the VDOM exists and actually building fast apps. Let's start with the most direct fix, Memization.
Right, memization, it's basically caching. Caching the result of a function, or in our case, a component, and only rerunning the logic if the inputs have actually changed.
And in the old class component days, this was built in, right, with pure component.
Exactly. If you extended React.PureComponent instead of React.Component, it automatically did a shallow comparison of the current props and state against the next props and state.
Right.
If nothing changed at that top level, it just skipped the re-render for that component and its entire subtree.
Super convenient. Now, most of us are writing functional components these days. How do we get that same automatic shallow comparison? Is it just wrapping our component in React.memo?
Pretty much, yeah. React.memo is
Right.
the functional component equivalent. You wrap your component export with it, export default React.memo my component, and it does the same thing. Shallowly compares incoming props. If they're the same as last time, render skipped.
Okay, simple enough.
Yeah.
But this reliance on shallow comparison that leads directly to what you called the mutation trap earlier.
Yeah.
Sounds ominous.
Huh. It can be. It's probably the single biggest gotcha with pure component and React.memo. Because they only do a shallow check, they're just looking to see if the reference to an object or an array prop has changed.
Right, not the contents inside.
Exactly. So if you have, say, an array of words in your state, and you update it by directly mutating it, like using words.push, new word, and then you call setState with that same array object, well, the reference hasn't changed. It's still the same array in memory.
So React.memo looks at the prop, sees the same reference as before, and thinks, nothing changed here.
Bingo. It skips the re-render. But the data inside the array did change. So now your component might be showing stale data, or you get weird inconsistencies. The optimization is completely broken because of that mutation.
Ouch. Okay, so the only way to make this work, to signal a change properly, is to always create a new reference.
Always. You have to embrace immutability. Instead of push, you use something that creates a new array, like the spread syntax. Set words, new word. Or for objects, set username, new name.
Every single time. You have to create new objects, new arrays for updates.
If you want memo or pure component to work reliably, yes. That new reference is the signal React needs for the shallow comparison to detect a change.
That's a really fundamental discipline shift if you're not used to it. Okay, super important. Let's shift gears a bit. Data transformation, especially thinking about Redux apps. People talk about Reselect a lot. What problem is that actually solving?
Reselect tackles the problem of expensive computations inside your Redux selectors. Maybe a selector filters a huge list, sorts it, derives some complex data.
Right, stuff you wouldn't want to do on every single render.
Exactly. But if you just use a plain selector function with useSelector, that function might rerun after every single action dispatch in your entire Redux store, even if the action had nothing to do with the data that selector cares about.
So lots of wasted computation.
Potentially, yeah. Reselect's createSelector function fixes this by adding memoization to the selector itself. It remembers the inputs, the specific pieces of state it reads, and the output, the derived data.
So if the underlying state slices it depends on haven't changed since the last time it ran.
It just skips the expensive calculation entirely and returns the cached result instantly. Huge performance win for complex derived state.
Nice. Okay, let's talk UI responsiveness, perceived performance. This next one sounds really interesting. Use deferred value. You said it's a game changer.
I think it is, yeah, especially for things like responsive input fields. Imagine you have a text input, and as the user types, it filters a massive list or grid below it.
Yeah, classic scenario.
Yeah.
And usually that can feel really laggy, right? You type, and the input stutters because the filtering is blocking the main thread.
Exactly. The traditional fix might be debouncing or throttling the input handler, which is okay, but it often feels artificial. You type, wait 300 meters, then the list updates.
It feels delayed.
Use deferred value is much smarter. It doesn't actually delay the work like debouncing does. It reschedules it.
Reschedules. How does that work?
So you get the current input value, maybe input value. You
Oh.
pass that to use deferred value, const deferred value, use deferred value, input value. Now you have two values.
Okay.
You use the original input value to update the input field itself immediately. So the user sees their typing happen instantly, no lag, very responsive.
Right. Prioritize the direct feedback.
Then you use the deferred value for the expensive part, like filtering the list. React understands that this deferred value is less urgent. It will still update based on input value, but React will let the urgent stuff, like the input field update, render first. The update using deferred value happens slightly later in the next available render cycle without blocking the initial interaction.
Whoa. Okay, so the input feels instant, and the heavy list filtering catches up moments later without causing jank.
Precisely. It keeps the UI feeling fluid during heavy operations. It's not delaying work. It's letting React prioritize the updates intelligently.
That's a really clever way to manage perceived performance. Okay, these patterns are powerful, but optimizing without measuring, that's just flying blind, right?
Absolutely. You need data. Optimization has to be data-driven, which means we need to talk about profiling.
Where do we start? What's the go-to tool?
The first stop is usually the React DevTools profiler. It's built right into the browser extension. You just hit record, perform the interaction in your app that feels slow, hit stop, and it gives you a breakdown.
And the key there is the flame graph visualization, right?
Yeah, the flame graph is super useful. It shows you which components rendered and how long each one took. The colors are the main clue.
Tell me about the colors. What do they mean?
Yellow components are the ones that took longer to render those. Those are often your primary suspects, your bottlenecks. Blue and green components rendered relatively quickly. And importantly, gray components are the ones that didn't re-render at all during that interaction.
Ah, so gray is good. That means your React.memo or other memorization strategies are actually working for those components.
Exactly. It confirms your optimizations are effective.
But sometimes things are trickier. What if a component is re-rendering, so it's not gray, but you look at the props and they seem identical? How do you debug that?
Yeah, that happens. Maybe an object reference changed unintentionally, or a function prop is getting recreated every time. For those really subtle cases, the why did you render library is fantastic.
Okay, how does that work?
It's a library you add to your project, and you can explicitly tell it to watch specific components. You might add myComponent.whyDidYouRender is true. Then, in the console, whenever that component re-renders unnecessarily, meaning React thinks the props changed, but maybe they were shallowly equal or there was some other subtle issue, the library will log exactly why it re-rendered, often pointing out which prop caused the issue.
That sounds incredibly useful for those head-scratcher moments.
It really is. You can also configure it to track all components wrapped in React.memo, which helps find issues across the board.
So we've got the profiler for the overview, and why did you render for specifics? What about proactive measures? Things we can do during development to catch issues before they even become performance problems.
That's where React Strict Mode comes in.
Right.
It's a wrapper you put around parts of your app, usually the top level, during development.
And what does strict mode actually do?
Its main trick is that it intentionally double invokes certain functions, render methods, effects, and others. It does this only in development mode.
Double invokes. Why?
To shake out impurities. If your component's render function has side effects, running it twice might make those side effects obvious. If your useEffect hook doesn't have proper cleanup, the double invocation can help expose memory leaks or other issues when the component mounts and unmounts quickly. It basically helps you find code that isn't resilient or cure enough.
So it's like a built-in stress test during development.
Kind of, yeah. It surfaces potential problems early.
Okay, one more tool. What if we need to zoom out even further, beyond just React renders, and see how the whole app impacts the browser's actual frame rate?
For that, you need to step outside React DevTools and use the browser's own developer tools, specifically the Chrome Performance tab or the equivalent in Firefox.
And what are we looking for there?
You record your interaction again, but crucially, you should use the throttling feature to simulate a slower device, maybe like 4 by CPU slowdown. Then you look at the FPS chart, the frames per second graph. You're looking for dips, especially red bars, which indicate the browser dropped frames and couldn't maintain a smooth 60 fps. Those red bars often correlate directly with heavy JavaScript execution, which could very well be your React app working too hard during rendering or effects.
Got it. So multiple layers of tools, from broad strokes in Chrome Perf down to specifics with why did you render?
Right. Use the right tool for the job.
Okay, moving into our final section here. We've optimized the runtime. Now let's talk about optimizing for production, for scale, for that initial delivery to the user. The goal here is minimal code, right?
Absolutely. Getting the smallest possible amount of JavaScript to the user upfront is key for fast initial loads. And the first technique here is tree shaking.
Which sounds cool, but what is it?
Tree shaking is a process handled by your module bundler, like Webpack or Rollup, typically when you build for production. It analyzes your code, looks at all the import and export statements.
Using that ES 2015 module syntax.
Yes, that's crucial. It figures out which pieces of code you've imported but are actually never used dead code, and it just removes them from the final bundle.
So it shakes the unused code out of the tree.
Pretty much. To make it work effectively, you need to be using ES modules, have your bundler set to production mode, and there's one more important piece.
What's that?
You can help the bundler by marking files or even entire packages as having no side effects in your package.json. You add side effects, false. This tells the bundler, look, if you import something from this file or package, but don't actually use the imported value directly, it's safe to remove the import entirely because just importing it doesn't do anything important globally.
Ah, okay. That gives the bundler more confidence to remove unused imports, potentially shrinking the bundle even more.
Exactly. It can make a big difference, especially with larger libraries.
Okay, so tree shaking removes unused code we did import. What about code we don't need yet? Code the user might only need later.
That's where code splitting comes in. This is probably the single most impactful technique for reducing initial bundle sizes.
How does it work?
Instead of bundling all your application code into one giant JavaScript file, you split it into smaller chunks. The most common way is route-based splitting.
So using something like React Router.
Yeah. With modern React Router using Create Browser Writer, you can use a lazy property on your route definitions. You provide a function that calls a dynamic import for the component associated with that route.
Like React.LazyPageComponent.
Exactly. React Router handles the rest. When the user navigates to that route for the first time, then the browser fetches the JavaScript chunk for that component. It's not loaded initially.
Dramatically cutting down that initial payload.
Hugely. You can also use React.Lazy and dynamic import for splitting out other large components or modules that aren't needed right away, even if they aren't tied directly to a route. Maybe a complex modal dialog or a heavy churning library.
Load it only when the user actually interacts with the feature that needs it.
Right. Defer loading as much as possible.
Now, all this lazy loading and dynamic importing means things won't be available instantly. How do we manage that? Show the user something sensible while they wait.
That's the job of suspense. Suspense is a component that lets you coordinate these loading states.
So you wrap the lazy loaded component.
You wrap the place where the lazy component will render with suspense fallback loading spinner. While the code for my lazy component is being fetched and loaded, React will render your fallback component instead. Once the code arrives, React seamlessly swaps it in.
So it manages showing spinners or skeleton screens automatically while the code chunks are loading?
Yes, and it handles orchestrating multiple lazy components within the same boundary. It creates a much more cohesive loading experience.
And you mentioned something about render as you fetch. Is suspense involved there too?
It is, although that pattern is still somewhat experimental or advanced. But what's fascinating here is that suspense isn't just for code loading. It's designed to eventually handle asynchronous data loading too. The idea behind render as you fetch is that you start fetching data and start rendering the component simultaneously.
Instead of fetch data, then render.
Right. You render immediately, and if the component tries to access data that hasn't arrived yet, it suspends, telling React to show the fallback. When the data comes in, React continues rendering where it left off. It can lead to interfaces that feel much more responsive because you're not waiting for data before showing anything.
Wow, that's a different paradigm. Suspense really feels like it ties a lot of these asynchronous pieces together.
It does. It's key to managing the complexity as your app scales and uses more lazy loading and potentially async data fetching.
Okay, so let's try and wrap this all up. If we distill this deep dive, it feels like React performance optimization is really this combination. You have to understand the core mechanics, right?
Yep.
The VDOM, reconciliation, why renders happen.
The fundamentals.
And then you need to apply these targeted strategic solutions, things like memoization with React.memo, being really careful about avoiding mutations.
Using new references always.
Using tools like Reselect for derived data, maybe use deferred value for UI responsiveness, and definitely being aggressive with code splitting and tree shaking for delivery.
That covers the main pillars, yeah. And I think the final takeaway for you, the listener, is that optimization isn't some magic checklist you just follow blindly.
Right.
It's really about diagnosing the specific bottleneck in your application. Maybe your app is heavy on calculations and better memoization is the key. Or maybe it's loading way too much code up front and code splitting is your biggest win.
Start with measurement. Use the tools.
Absolutely. Profile first, find the biggest fire, put that out, then measure again. Don't guess. Target the bottlenecks.
So, really performant React apps, they only render what absolutely needs to update, and they only load the code that's necessary right now. It's about being deliberate.
Deliberate and data-driven.
Which leaves us with a final thought for you to ponder. What's one consistent small improvement you could implement, starting today? Maybe it's adding React.memo somewhere obvious. Maybe it's fixing one mutation pattern. Maybe setting up basic code splitting that would compound over time into significant performance gains for your users.